All right, hey everybody. Thank you for coming this morning. I have the honor to introduce Bandt Espigule. Please welcome them.
That I'm not physically here enjoying your reunion, but I'm glad that I'm going to be sharing with you some of the latest results I got. And actually, this project started at ICERM somehow, and I'm going to be talking about this hidden geometry of polynomial roots related to self-similar sets, collinear ones. So they have the n level pieces are collinear, and I'm doing this as part of my PhD at the University of Girona, under the supervision of Juher and Saldaña and Juher, and I'm very grateful that I managed to do that as a sub-project of the PhD thesis. So let's jump. So I'm talking basically in Figueres, that's the hometown of Salvador Dalí. Myself, from that part of the Mediterranean Pyrenees, I also got interested in geometry. I started when I was 16, taking photos the whole summer, and also trying to understand the formal function, and reading the books of Mandelbrot and other people. But it was later when I was able to start to program that I was at the University of California in Santa Barbara, and I took an elective that was called California Physics. So they allowed me to have a little project. And back then I was reading this paper that was just published about vascular plants. And the leaves of these vascular plants have these redundant loops, and these loops would make them more resilient against bugs eating some parts of it. So the memory is more resilient. So I just do mathematics and started to play with it and get some resolving patterns. But this little project at the end of my stay at Santa Barbara sparkled an interest in understanding these kind of geometrical objects. And it was in Frederick when I closed this loop, the right branch is looping and taking and getting this point. And it's when I started to read the classics, Cantor, and also the middle field Cantor set, and also the why Podkosh was interested in finding a geometrical analog of the Petras function. So he came up with that because of his geometrical information, and he wanted to recreate this kind of non-differentiable curve, but using just geometrical shapes. If you intersect one of the boundaries of this Koch curve, you get the middle field Cantor set. So understanding all the conditions with these classical fractals was very insightful, and Paul Levy took the Koch curve, and he was handling this when he in his 20s, and he was imagining unfolding these triangles to get this fractal curve. It was looping itself, it's known as the C-Levy curve. If you change the angles, you get other curves like this curve corresponds to the Pythagoras B that's very popular in just some websites, including some fractals. So Paul Levy was actually a professor of Mandelbrot. In one of his books, he actually describes himself as a disciple of Paul Levy. And then the connections with dynamical systems that I was interested in back then, and with this complex dynamics, was very inspiring. But the paper that was very insightful was this introductory paper in the mathematical intelligence that's very beautifully illustrated. It's very layout, so I recommend taking a look at it. It's from the 1999, and Mandelbrot collaborated with Michael Frame at Yale, and they published these results there. And actually, it was simultaneously when Stephen Wolfram was also working on these binary subconducting trees. And then there was a PhD thesis by Tara Taylor about this extension of the article. And that's the starting point when I was using Mathematica to understand them. So these are one of the ideas animations I did. So the thing that they are looking for each angle, the ramification, they look for the critical ratio, scaling factor, that gives you a corrected tip set. So here the leaves are Cantor set in the plane, but then when you find the right ratio, you get a just connected tip set. And then when you change the angle, you have to change the ratio, and there are two critical angles where you have a dimension 2, and they have these topological changes when they pass through. And in this area, you get the Gauss curves as the tip set of the trees. So after a few weeks working on that project, I managed to work out the generalization of from binary to n-ary trees. And that was a very nice moment when I was capturing all these phenomena and having a big picture about how they sub-intersect and what are the equations describing them, and also seeing the small symmetries. And when these transitions in topology happen, was very interesting. So here I'm going to show you the animation for the ternary case when you have the self-contact, and there is a few critical points when you have these changes. So this, you can consider that as a generalized Gauss curve for the ternary microsymmetric tree. So I managed to publish these two results, one at Bridges and the other one at the Symmetry Festival, both happening in the Netherlands in 2015. And the project was developed thanks to the mentorship of Susanne Kromker at Heidelberg University. When I was there, so I looked for someone working in fractal geometry when I started to my Erasmus there, and I found her work on the these models, but he had a very physical sculpture in the building is there, and you can actually see, you visit the institute. And when I contacted her, she was very keen to accept my proposal as a project, also following some of the guidelines what Taylor did with the PhD thesis about the binary case and extending it to the binary case. And she also encouraged me to build a website. I chose the Wolfram computational document format to have it in the interactive. And that was also a way to get me into the Wolfram Science Summer School that same year when I finished the studies. And they offered me a job there, so I was actually interacting with Chris Carlson, Michael Trott has one of the earliest visualizations of this in the Wolfram demonstration project. And it's about, instead of having the mirror symmetrical case, you have one branch that's 180 degrees opposite to the other one. So this corresponds to the sums of differences of all power series with coefficients 1 and -1. So that's what I'm going to be talking today. And this is the binary case, but we're going to see also the n-ary case for these collinear sets. So the mirror symmetrical case, I designed quite well during these 2 years at Heidelberg, but then I was interested in connecting that to the known literature about these sets of connectedness for the binary case of 180 degrees, and that corresponds to the older roots of polynomials with -1 and 0, 1 and 1. So, but back then I started working for them, and I didn't manage to actually contact Christoph Banner or some of the experts on that. Boris Saldaña was also working on that. But the seed was planted because Bill Thurston, in one of his last projects, he worked on a related project. He was well aware. He was very active in math overflow before he passed away. But he was looking at the John Bandt blogs, and he was well aware about this connection. Here you have him with all the manipulates and mathematical explorations he was doing back then. It was presented in the checklist 2018, and I saw the space of this object that he was studying is connected to these roots of polynomial tools with -1 and 1. and the notes that he didn't publish before passing away, but the paper was posted in the archive, and then John Milner added some extended notes, and it was published in 2014. Also, Sarah Koch was assisting in that process, and then in 2014 he joined forces with Danny Caligari and Alan Walker, and he did a very interesting study on the Saldaña sets of this binary case. So it has a long tradition. I mean, it is 55 years of work related to the binary case, but they prove a conjecture, which was the density. But at the same time, as a PhD student back then, Stepanos Silvestri, basically in the US, he was working on the same set. And then he saw my website and he contacted me. And that was when I was doing a big sabbatical from Oxford in 2017. And I decided to contact Núria Fageia at the University of Barcelona. So I did my master there with the group. And it encouraged me to just go back to academia and get some of the insights I got from the binary case, the arithmetical case, to the polynomial case. So that's one of the structures I was trying to understand the interior by looking at these three structures. As you saw the problem for the case. So that the basic idea is that you have all the input nodes described by polynomials, and then so the master thesis I showed that if you have a collision between two nodes, then you have a connectedness deep set, and also it corresponds to a root of a polynomial with coefficients with -1, 0, and 1. So that's one of the plots I showed you in ICERM. That's when you start to increase your roots, then you get these nice maps, and this is bounded in the disk of radius 2. And the idea is that the bigger is the root, I mean the size of the dot, is the smaller is the degree, and it also corresponds to one of these piece-to-piece intersections. And here at ICERM, I was reprinting these structures in 3D to see how the pieces intersect. And I'm also trying to prove that when you are also intersecting the branches, not only the nodes, you are in the interior. So from that, I got this internal structure of the interior that connects from one root to the next one when you increase the degree. And you have these algebraic tracks coming from root to root. And this is part of the structure of the connectedness locus. The whole set is structured this way. And now is when I'm going to be showing the big picture and how to prove that this is actually part of the set. And here's the quote of John Anderson that is very motivating, just to have this internal insight of the set. And also, if you change the perspective, here I'm going to be changing the parameter. Instead of x that is smaller than 1, we'll take c as a parameter, and it's going to be bigger than 1 outside the unit disk. So you define your digits, so the pieces are going to be placed from -n plus 1 to n minus 1. For the binary cases in -1 and 1. But then if you take the ternary case, it's going to be placed at -2, 0, and 2. The idea is that if you take the Minkowski sum of the binary case, you take the 2n-1 case. And during the process, if the binary case is connected, this Minkowski sum is like sweeping one against the other, so it's like painting it. And the process is going to be generating an interior region. And you can actually prove that this region is a parallelogram. And it contains the interior, in its interior it contains the initial branch that goes from -n plus 1 to n minus 1. And in the 2n minus case, it's going to be 2n minus 2 and to minus 2n plus 2. So the thing is that the images are also contained in the interior. So the tree structure is going to be giving you the information for connectedness, because there is this segmentation. If the parameter 2c is in the 2n minus 1 case, then the n case is connected. So we change from the connectedness condition to a membership condition. So to certify connectedness, we look for the 2c membership, and that's when we get the connected case for the binary one. So this is one zoom from the latest. Is also I'm going to switch to the website I built. So initially I did this algorithm in Mathematica, but recently in the past few months I built up an interactive website using WebGL, which is way faster. And here I'm pointing you to this parameter that corresponds to this Gaussian fractal that we were showing before. So that's the object there, and that corresponds to the Gaussian fractal. But here we have two copies, and the middle one is the intersection of the two pieces. And the thing is that the 2n minus 1 case, we are placing in one of the nodes. We know that it's connected, and now because it's part of the interior, we can perturbate this parameter, and we can stay in the interior just by sliding through this branch. And as we do, we're moving from here to this other node that also corresponds to a root. So we are tracking these algebraic curves that connect from root to root, and in a very nice way. And so we can approach the boundary just by giving sliding to higher order level branches. So back to the presentation. So the idea is that if you are in a root, then you know it's connected, and the Minkowski sum is going to be certifying that you have a rectangle, a parallelogram in this case, and the image of it, it's also trapping the parameter 2c. So it's going to be stable in this region. So we have these internal components for each root of the set, and you can advance and get higher degrees roots and approach the boundary. So here I'm going to be showing also what the insight that you get. The connectedness locus of the binary case is going to resemble the ternary case, which is the 2n minus 1. And so I'm going to be showing you when the parameter 2c is in the boundary of a self-similar set for 3 pieces. And that's when you see that if you look at this disk, it's going to resemble the actual shape of the ternary case. This is a synthetic self-similarity. Now you can increase the number of copies instead of binary to binary, and then you are getting these sets of polynomials with more and more digits, integer digits to play with. And the Minkowski sum of the binary case with the binary case is giving you the n plus 1. And in some particular algebraic numbers, you get these nice properties. For example, if you take the ternary case, one of the spirals, then you get this fractal dendrite. It's simply connected. And when you sum the Cantor set for the binary case, the result is the quaternary case. That it's a plane filling collinear fractal. These are also known as reptiles of the plane. So these algebraic numbers for the quaternary case, it's when the modulus is the square root of 4. Then you get the fractal dimension is 2, and then you can find these dots that I'm showing for these disks that they correspond to tiles of the plane. And so the key result that was published in our last paper in December was about proving this interior region, not with Minkowski sum, but using a covering lemma. So the intuitive idea is the following. So let me show you the parameters locus. And instead of using this parallelogram that's obtained by making the Minkowski sum, I'm using now this rectangle that just following. So the idea is that inside this lens region, you can take a parametric rectangle. That's actually the vertices are described by the following formula. So that's a vertex, it's a parametric rectangle that changes with your parameter C and N. And then what you get is that the case 2n minus 1, the 2n minus 1 pieces, the pixel images, are going to be covering this rectangle if you are inside this lens region. So when you're like moving away from these level sets, you're always going by level inside this region, because it's always covered by the following images of the initial rectangle. So these levels here are covered by the other ones. And then if you're trying to scale, you're going to find the next level. So you are getting this interior level set structure. And what we proved is that starting in n equals 21, this lens shape is covering totally the set. So as we increase the number of pieces, when we get when 21, we already scale to the lens. So here you have this big antenna, minus 21 and minus 21. But then the whole set is inside this lens shape. That's when you get.
I'm sorry to interrupt, but we're over time. If you want to have a quick question, if you could wrap it up now. Yeah,
so I'm going to close now. So the thing is that now we get this internal structure by level sets, and that was kind of surprising. And I'm going to be explaining more things about that next year in Paris. That's all I have to say. Thank you very much for your attention.
Time for a quick question. Okay, all right, let's thank our speaker again. Thank you.